So this particular modulation, I have been working on it for the last 4 or 5 years. So it is a result of a lot of work that I have done in the last 4 or 5 years. It's a new type of modulation which I will introduce in more detail today and tomorrow, which achieves much better performance compared to your existing OFDM, which is there in the standards right now. And so I will not be needing a lot of background. Okay, I guess most of the people are either undergraduate or postgraduate, right? So if you just listen to me, that should be enough. Okay. So I've organized day 1 like this. Initially I had sent something, but I realized that this is only a 2-day and not a 4-day. So I've just kept the basic, most important stuff. I have all the slides, but I'll see if I can go faster than. So I will also appreciate if this is very interactive, which means that if you're not able to understand something, then you just stop me at that point, and so that I can clarify your doubt. So session 1 is more of an introduction, wireless channel representations, why signaling in the time frequency domain is not appropriate when you have channels which have high delay spread and Doppler spread. I define something called predictability of modulation waveforms, and then I'll show why your usual pulse train that we always know about, that's the solution to how to achieve good communication when your channel is doubly spread. And then session 2 is going to be a little longer, so that's where I introduce this new signal processing paradigm. All of you are very good in doing signal processing in time and frequency domain, right? You might not have heard about delay Doppler domain, right? So I'm going to introduce that in the second session, basically. So this will be the first session. I just have this slide on 6G. I think what is important for us to know about 6G is what is going to be basically new as we go from 5G to 6G, right? So if you see this inner triangle over here, that's basically your 5G, which is based on IMT 2020 guidelines. And you had these 3 corners: URLLC, enhanced mobile broadband, and massive machine type communication, right? Now when you go from 5G to 6G, along with these 3, you already have these 3 here, okay, in 6G also, but you now got these 3 new pillars, okay, and these 3 new pillars are, one of course is ubiquitous connectivity. What that means is that no matter where you are, okay, whether you are in air or in sea, in a desert or in a mountainous area or in a rural area, not in a main town, you should be able to get reliable and high speed connectivity irrespective of wherever you are. Okay? Right now if you go to the countryside, the moment you start leaving your city limits, you will see that your phone will go, the number of bars will come down, right? You will get poor coverage, and you might even go down from 4G to a 3G or a even 2G connection, okay? So, and that's because the service providers don't think that it's economically feasible for them to go and set up their network in rural areas where the population density is not that much, right? So this is one of the points. The other is, of course, how do we leverage AI and machine learning, okay, to kind of improve the efficiency of the networks today. My take on that is that for AI and machine learning to really work, AI is going to make decisions about resource allocation, right, traffic management in the network, things like that, right? But for it to do that efficiently, it needs to kind of predict what the channel is going to be, several maybe milliseconds down the line, right? The problem with time frequency signaling is that when you have delay and Doppler spread, especially Doppler, then the channel is changing in time, right? So it's very difficult to predict. So if you can't predict, then it's not so meaningful to talk about doing machine learning and AI, right? Because you base your prediction on your current estimates. By the time those algorithms are applied, the channel has already changed, right? So that is one problem with this thing. And the third is, the third pillar there in 6G is integrated sensing and communication. Okay? And what that is about is, they are saying that you will make each mobile phone will also go and give sensing capability into it. So it becomes kind of a radar also. You know what is your immediate environment, and that has several benefits. The problem is that, in the current OFDM, the OFDM waveform is not really suited as a good radar waveform, because it is just a sinusoid, right? And sinusoids cannot, effectively measure delay, because you take a sinusoid, you delay it by something, it's still the same sinusoid, right? Its frequency doesn't change. So they are not good waveforms. We need, and the solution, the standards, is evolving right now. Standards meeting will be starting, very soon on what should be the waveform. I think we should choose a waveform which is good for both communication and sensing. And in such a way, because it should be like you mix your sensing and communication signals in such a way that they don't interfere with each other, and also that when I add sensing capability to an existing mobile terminal, it should not be like it's an overhead. It should not be like you are giving a dedicated part of your resource for sensing. It should be overlaid on top of each other, because otherwise it will become an overhead, right? And your actual data throughput will suffer. So those kind of things have to be kept in mind. This slide is just showing that as you went from 4G to 6G, 5G to 6G, you get this new kind of channels where, the delay and Doppler spread is much higher. Earlier, and also remember that we are also going to higher carrier frequencies. Earlier you were around 2G, now they are talking about even communicating earlier you were around carrier frequencies of around 2 gigahertz. Now we are talking about 7 gigahertz, right? So if a Doppler of maybe at 2 gigahertz you will experience 200, 300 hertz of Doppler, but when you go to 7, it will be 3.5 times more, it will be close to 1 kilohertz, right? And that can hurt the performance of CPU FDM. Okay? So these kind of, and of course, for ubiquitous connectivity, people are already talking about LEO satellite based, non-terrestrial networks, right? Because they can span the entire geographical area, right? So, but then with LEO satellites, you will get high Dopplers, right? Because, compared to the GEO satellite, LEOs are going to be traveling much faster relative to Earth, right? So naturally their Dopplers, because of them, is going to be much higher. So the question is, how do we tackle that, right? And then you have UAV channels and other ones which are going to come there in 6G. Okay, so So this is about, we'll be talking a lot about wireless communication, right? So wireless communication is not like wireline. Wireline communication means there's only one path for the electromagnetic signal to go from the transmitter to the receiver, which is along the wire, right? But when it's wireless, then the signal can travel through different paths, right? Suppose I'm the transmitter, you are the receiver. One is just the direct path, the other could reflect from this wall, another part could reflect from that wall. So it's a multi-path kind of a channel. And what I'll be assuming is that if this is my passband signal XPT, okay, passband means that it's in the higher carrier frequencies. My received signal is RPT, then this is the channel model basically, that I mean, your receive signal is a sum of what you receive along this capital P number of paths. Along the ith path, your signal that you transmit is delayed by some seconds, okay, and that delay itself is kind of time varying, okay. That's why I've shown it as a function of t, and that will happen when consider a mobile situation, right, where you have a stationary. Let's say you're talking on your phone, and as well at the same time you're also moving in a car, right? So then your distance from the base station is also increasing with time, right? And because of that, the delay will increase with time, right? So that's why the delay is a function of time. So the delay is the distance divided by the speed of light. The distance, ith distance is di, and I mean let's assume that your relative speed with respect to the base station is vi, then the distance at time t is given by this equation. Okay. Let's say that you are sending a packet in this time interval 0 to capital T. This is your bandwidth, okay, and I'm assuming narrow band kind of a communication where your bandwidth is much less than the carrier frequency, because usually this B will be in at most maybe 100 megahertz, something like that, but this will be several gigahertz, right? So this model is true. And then throughout the lectures, we will be only focusing on the complex baseband representation, okay. So for XPT, this XT is the complex baseband representation. For RPT, RT is the complex baseband representation, okay. So this equation, when you write it in terms of the complex baseband, then you get this kind of a model. So the complex baseband equivalent of the received signal will be given by this, basically. So you have some complex channel gain. So the ith term in this summation is basically what you receive along the ith path, ith channel path. So your x t is what you have transmitted. Again, x is the complex baseband equivalent of the actual passband transmitted signal. You have a delay on it, and then you have this term, which is basically your Doppler shift, right? So this nu I here is basically your Doppler shift, okay, and that's given by your carrier frequency times the relative speed along that ith path divided by the speed of light, okay. So this is the model that I'm going to follow throughout this short course. Just to give you an example, assume that you have a base station here, you have this user equipment, your mobile phone, okay, and you have 4 reflectors, reflector 1, reflector 2, 3 and 4. 1 and 3 are stationary, 2 and 4 are mobile reflectors, okay. I've assumed that the base station and the user equipment are both static, they are not moving, but then the reflectors are moving, right. Even if your reflectors move, you will still experience Doppler, right. So the signal that you receive along the ith path is using that model, it's given by this equation. This is the delay shift, this is the Doppler shift to the signal, this is what you receive, complex baseband equivalent. And as we discussed before, this channel model is not, you cannot model it as a linear time invariant system. It's linear, but it's time varying, okay. So that's the important thing to be kept in mind here. And then there are different representations. One is this representation is called the time delay representation of the channel. It's given by h t comma tau, and looks something like convolution, which already all of you know, right. For LTI channels, the input output relation is given by the convolution, right, convolution with the impulse response of the channel. Now in this case, what happens is this is the convolution integral, but the impulse response is a function of this time t, okay. I mean if it becomes, the special case is when you have a linear time invariant channel, okay, and which will happen when these nu i's, if you see in this equation for the impulse response, it depends on the time t, right. That's why I'm calling it as a time varying impulse response, right. But if you make these nu i's to be 0, if there is no Doppler, then this term will become 1 and your impulse response will become this. But this obviously does not depend on t in that case. And this is your usual LTI channel model, right. And then there is this time frequency model also, and what that says is that the signal that you receive in time can be written as the Fourier of. So basically the signal that you transmit, if you look at the signal in the time frequency domain, okay, then the effective channel in the time frequency domain is this HTF, okay. And again you see this dependence on t, okay, and of course there is a dependence on f also, right. Even when you have an LTI channel, the channel does vary along the frequency domain, okay, right. So the special case is when you have an LTI channel, and in that case the dependence on t goes away, and this is the response of the channel in the frequency domain. It's basically the Fourier transform of your impulse response, right. But this is the more general setting, okay. So when you have a time varying channel, then the frequency response is, again it's like this equation, if you see, is like a Fourier transform of the time varying impulse response, right. And that is why you have dependence on time and frequency. So in general, the channel is changing in time and frequency, okay. In time and frequency it is not static, it is changing, that is the main idea. And I have just plotted it here for this 4-path channel, and you see the magnitude. So what I have plotted is magnitude of this quantity, and you can see it is not constant, it is not like flat, it is changing along time and it is changing along frequency also, okay. In fact, if you go back to this equation, okay, and for h t tau, if you use this, okay, if you place it here, this is what you get. So you will see that there is a term which corresponds to time variation, okay, and there is a term which corresponds to depends on f, okay. So this will cause you the variation in the frequency, okay. How quickly your channel changes in time will really depend on this nu I, right, because if this nu I is large, then it will change faster in time, right, and if it is small, then the channel varies slowly in time. Similarly, how fast the channel varies in frequency depends on these delay spreads, on the delay spread basically. If the delays, so what basically matters is the coherence time. Coherence time is approximately the time over which the channel does not change that much, and it is inversely proportional to the spread in the delay, which is basically the maximum minus the minimum Doppler among all your paths, okay. So if the Doppler spread is large, then your channel will be really changing very fast in time. If your delay spread again is very high, then again your channel will change very fast, not in time but in frequency, okay. So that is what I call as the coherence bandwidth. Coherence bandwidth is the bandwidth in time, in frequency, over which the channel does not change that much, okay. So these are some very basic concepts that many of you already will be knowing, right. So far what we are taught, and the theory is well established for how to communicate on linear time invariant systems, channels, right, where you only have delay, right. The theory is well established for that, and the theory is basically, it is optimal to send information on narrow time domain pulses, right, and that is what used to happen in TDMA and CDMA in 2G and 3G, right. We were doing TDMA, right, you were sending information on narrow time domain pulses, right, and then later on we had OFDMA, where you are actually sending information on sinusoids, okay. So that is also okay. We know how to communicate reliably on when the channel is LTI. The problem is that when the channel is not LTI, then all this theory is going to break down, right? When the channel is time varying, then this theory is going to break down. But what do we do now? What we are doing now is kind of an ad hoc way of using that LTI theory on a channel which is not LTI, right? The moment you have Doppler spread, you anyways have delay spread even in LTI. The moment you have Doppler spread, it becomes doubly spread. And what they do now is, at least in the standards in OFDM, is that they kind of sense or estimate the channel periodically in time and also periodically in frequency. Okay? By doing that, they ensure that between any two estimation epochs in time, the channel doesn't change that much. Okay? So, you will typically kind of estimate at least once every coherence time interval. Okay? And so, you kind of assume that between these two sensing epochs, the channel did not change that much. So, it was almost like LTI. Okay? But this is not the theoretically best way, optimal way to communicate in this kind of channel. It's only a fix. It's only an ad hoc arrangement, right? And the problem with this fix is, I've tried to explain it here. So, I have a resource here which is roughly 1 millisecond in time and around 720 kilohertz in bandwidth. Okay? And I am using cyclic prefix OFDM, which is there in the standards. Now, assume that I have a Doppler spread of 1 kilohertz, okay, maximum. Now, when I have a Doppler spread of 1 kilohertz, see, because of the Doppler spread, in the frequency domain in OFDM, you are sending information on different subcarriers, right? Because of Doppler spread, one subcarrier will start interfering with the next subcarrier, right? But if the spacing between the subcarriers is large enough, then it is not a problem. Then ICI intercarrier interference is not much of a problem. And so, what in OFDM we are going to do is we make sure that the subcarrier spacing is at least 10, 15 or 20 times more than your Doppler spread, and this is a rule of thumb. Okay? So, let us say I choose my subcarrier spacing to be 15 kilohertz, which is sufficient for 1 kilohertz of Doppler. That corresponds to a time symbol duration of 1 over 15, which is 66 microseconds. And then of course, you add a cyclic prefix. The cyclic prefix is there to take care of the delay spread of the channel, so that two adjacent symbols in time do not interfere. And then, as I said, these red resource elements are basically your pilots. So, you are putting pilots along time periodically, if you see, and also along frequency, okay, periodically, right. And the pilots are an overhead because you are not transmitting data on those resource elements. And in this example, this overhead is around 4%, which is not that much. The cyclic prefix is also an overhead, but it is smaller compared to the symbol duration, it is around 3% or so. Altogether, you have an overhead around 8%, which is okay, which is manageable. But now assume that you are in a scenario where now your Doppler spread increases from 1 to 4 kilohertz. Okay? Once it goes to 4 kilohertz, you cannot use 15 kilohertz spacing, because then you will have very severe inter-carrier interference, right? So, that is not a possibility, right? So, what do? You have to increase your subcarrier spacing, you make it 4 times larger. So, you make your subcarrier spacing to go to 60 kilohertz, right? The problem with that is when you make it 60 kilohertz, your symbol duration shrinks by 4 times, but the cyclic prefix has to remain the same because the channel delay spread did not change. The channel delay spread is not in my control, right? And therefore, the cyclic prefix overhead becomes 15% now, which is very significant, right? Also, because you have a higher Doppler, see, you have to pack pilots along time more frequently. So, the pilot overhead increases to 12%, and altogether the overhead is close to 28%, which is a lot. Okay? So, this is what I said. I mean, in current 4G, 5G, the Dopplers we are experiencing is not much, and that is why the overheads are not that much. But the moment you go to these very high Dopplers, it will not work, right? Your overheads will simply become too large. Okay, I wanted to explain this in more detail where the problem is when you do time frequency signaling. So if you say, I take the 4 example again, and let's say I want to use time domain pulses to do my communication. Okay, so what do? You transmit a time domain pulse initially to estimate the channel, right? So you do that, and here I am assuming that reflector 1 and reflector 2 have exactly same delay of 2 microseconds. Then what will happen is, what I receive here from the brown and the blue reflectors, they will sit on top of each other because the delays of these 2 paths is exactly the same. Okay, and I cannot distinguish between them in time domain, right? Of course, for the 3rd and 4th reflector it will be like this. So for the user it will appear as if there are only 3 reflectors and not 4. Okay, and then you estimate the channel. So at a tap of at a delay of 2 microseconds, you estimate the channel to be equal to H1, which is because of this first path from the first reflector, plus H2 times e to the j 2 pi nu 2 times T0. Okay, nu 2, because you get this term because of the fact that this reflector 2 is mobile. Okay, so this is the complete channel estimate for this tap, the tap at 2 microseconds. Okay. Now later on, now that you have sensed and you estimated the channel, you start sending your information on the other time domain pulses. Okay, so let's say on this pulse at time t1, you send some QAM information symbol. Okay, you again receive 3 reflections. Okay, and obviously you will combine them and you will make an estimate of the QAM symbol that, and for combining them you need to know the channel estimate, right? The problem happens that the channel for this pulse which you receive after a delay of 2 microseconds now is different. H1 is as it is, but this other term has nu 2 times T1 because this pulse was transmitted at T1, right? That is what I mean when I say it is a time varying channel. So the coefficient for the second lag, you had estimated it to be this complex number, but when you transmitted your pulse it became this complex number. And that will cause problem for you because now you cannot combine them appropriately, right? You will get errors, right? So somebody can say that, okay, let us do this thing. Why don't we, if you want to separate these 2 reflections, we can examine this received response in the frequency domain, because this is coming from a Doppler shift, whereas this is no Doppler shift. So maybe in the frequency domain we can separate them. But it is not possible because when you look at the Fourier transform, because it is a narrow time domain pulse, in the frequency it is everywhere. So there is no way that if it was localized in frequency, then we could have said that, okay, then you could have seen the difference, because for reflector 1 it will be there at that same frequency, for reflector 2 its frequency will increase by nu 2, which is the Doppler shift of reflector 2, right? But that you can't do because this is a narrow time domain pulse which is everywhere in frequency. Its Fourier transform is 1 everywhere, right? So that's the problem. You'll get into a similar trouble if you send information on sinusoids. Sinusoid is a pulse, any sinusoid is a narrow pulse in the frequency domain, right? So let's say I send let's say I send a pilot, okay, because again in the frequency also the channel is not constant, right, it's varying. Suppose on this subcarrier F0 I send a pilot, okay. Now reflector 1 and reflector 3 are both basically 0 Doppler shifts because they are stationary. So I will get reflections from the brown and the green on the same subcarrier because they are not introducing any Doppler shift. You get the reflections on the same subcarrier on which you transmitted your pilot, right. But then because they have different delays, reflector 1 and reflector 3 have different delays, you will get these different exponentials there, okay. It's the same thing, I mean your channel is also changing in frequency, right, because of the delays, right. And you estimate the channel on this subcarrier F0 to be this complex number, right, the sum of these two, right. Again, at f0 you cannot distinguish between reflector 1 and 3 because they just add up, right. I mean, for example, if you had another static reflector, that will also add up and come there, right. So, you do not even know how many reflectors are there on that subcarrier, right. So, this is the estimate that you get, and then let us say you send a QAM symbol on some other subcarrier f1, but there the estimate of the channel will be different because f1 is not the same as f0, right. I mean, the channel is also varying along frequency. There the channel coefficient at f1 is going to be this number, okay, and there is no way by which, I mean, you know this because you estimated the channel on f0, but using this you cannot estimate what is the channel on the other one. There is no way you can do that, okay. I mean, the same thing is actually true here also. So, even here if you know this, which was the channel at time t0, you cannot predict what is the channel at time t1. It's not possible because, I mean, if you see this complex number has so many parameters, right, it's just one complex number. From that you cannot find all these 3 different unknown parameters, right. So, here also in frequency you get stuck with a similar problem because you cannot separate out reflector 1 from reflector 3, right. Now, you will say that okay, reflector 1 and reflector 3 have different delays. So, if I look at the received response in the time domain, maybe I can separate them, but you can't do that because you are sending a narrow frequency domain pulse. In the time domain it is spread everywhere. So, you again get stuck, right. So, the basic problem is that, so the basic problem is with time domain pulses, they are localized in time, but then in frequency they are spread everywhere. With frequency domain pulses, they are localized in frequency, but they are spread everywhere in time. I need something which is kind of simultaneously localized both in time and frequency, only then I can separate all these reflectors, right. Now, I wanted to define something called predictability. So, I mean, as you know, you take any modulation is just a collection of carrier waveforms, right, and on each carrier waveform you send a QAM symbol basically. I say that a modulation is predictable if and only if from the response of the channel to a particular carrier, let us say I choose one of the carriers out of all these so many carrier waveforms and I transmit it, I record the response of the channel to that particular carrier. From that response, is it possible to accurately predict or estimate the response of the same channel to all the other carriers, okay. If I can do that, then my modulation is predictable, right. For example, when I have an LTI channel, right, it is predictable. I mean, I can just send a time domain pulse, okay. If I send a narrow time domain pulse, I measure the impulse response. From that impulse response, I can exactly tell the response of this LTI channel to any other input, right. But the moment you have mobility, time domain pulses, the modulation of all possible time domain pulses is not predictable, because if you look at the response of a particular time domain pulse at time t0 to this kind of a Doppler channel, from that response you cannot predict the response of the same Doppler channel to a time domain pulse which you transmitted at some other time t1, and we saw that, right. So, time domain pulses as a modulation is not predictable when the channel is doubly spread, but if the channel is only delays, then time domain pulses, then it is a predictable modulation, right. So, that is what we mean by predictability, okay. Similarly, if you have a doubly spread channel, then frequency domain pulses are also not predictable by the same thing. And the reason I said why they are not predictable in doubly spread channels is because they are not kind of simultaneously localized in both time and frequency. That is the main problem. But then, I mean, all of you know that there is this Heisenberg uncertainty principle which says that you cannot simultaneously localize a signal both in time and frequency. If you try to localize in time, it will expand in frequency and vice versa, right? But we have been able to kind of go around this, principle without, of course we cannot violate it, right? But we can do something which makes the signal look almost like quasi-localized simultaneously. It's not really localized, it's quasi-localized. And that is what this is. All of you have studied this pulse train, right? When you teach this chapter on sampling in your signal and systems course, then you teach the students, and the students are taught about using the pulse train, right? And that's the waveform. If you look at the pulse train, so here I have shown a pulse train where you have pulses every tau p seconds, okay? Now the Fourier transform, if you look at this waveform, it is not localized because you don't have one pulse, infinitely many pulses from minus infinity to plus infinity, right? But if I only look in a small time interval of tau p seconds, then there is only one pulse, okay? So in every interval of tau p, it is kind of localized, okay? If you look at the frequency or the Fourier transform of the infinite pulse train, that's also a pulse train in the frequency domain, right? But of course the period is equal to the inverse of your delay, time period, right? And time period was tau p. In the frequency domain, your period of these pulses will be 1 over tau p, right? But it will still be a infinite pulse train. And if you look at any interval in frequency of, let's say, of bandwidth nu p, you will see only one pulse. You take any interval here of length nu p, you will only see one pulse. So in that way it is actually localized, although it is not exactly localized because we have infinitely many pulses. So this kind of a waveform is what I have shown is ideally suited for communication in a doubly spread channel, and I'll try to motivate that. I'll go back to the same 4-path example and show how it's going to solve the problem. Now what happens when you actually, so this pulse train, when you transmit it through a channel, what happens to it? So suppose there is a channel and there is only a single path, just to make it simple to understand. And suppose that single path induces a delay of tau 0 and a Doppler shift of nu 0. So what that will do to my pulse train in time is that it will first introduce this delay of tau 0, okay. So earlier, let's say my pulses were located at time 0, tau p, 2 tau p, like that. After the delay at the receiver, it will be located at tau 0 plus tau p, tau 0 plus 2 tau p, like that. And because of the Doppler, it will get multiplied with a sinusoid of frequency nu naught, right. So this is the kind of waveform that you will actually receive through that path. And these are actually, these are what I am going to make as the carriers for ZAC OTFS modulation. These are going to become carriers because you start with your standard pulse train and you can give it infinitely many delayed Doppler shifts, because tau naught, nu naught, it can be any pair of real numbers, okay. So you give all possible shifts, you get infinitely many carrier waveforms, okay. And all of them together, that's my ZAC OTFS modulation, okay, roughly, okay, but we will come to it in more detail. And I will show later, and so each one of these, delay and Doppler shifted waveform, I am calling it as a pulse-on because it's actually a pulse train which is modulated by a tone, by a sinusoid. So pulse train and tone is pulse-on, okay. So it turns out that these pulse-ons, they form a predictable modulation, a predictable set of carrier waveforms. If you estimate, let's say you send one of these pulse-ons through the doubly spread channel, and you look at the channel output, you record that channel output. From that channel output, you can predict the response of the same channel to any other pulse-on corresponding to any other tau 0, nu 0. That's the beauty. basically. So that's why it's predictable. Okay. But of course, predictability up to an extent, your tau naught should not exceed tau p. Otherwise, because beyond that it's the same thing, right? So there's an ambiguity, right? Similarly, nu naught should not exceed nu p. So as I said, it is localized only till tau p and nu p. That's what I mean when I say it's quasi-localized. Okay? Now let's see how this pulse-on will allow you to separate the channel paths. Okay? Now in the first case, when we were transmitting these time domain pulses, if you remember, there were these two reflectors 1 and 2 which had different Dopplers, but the delay was the same, and therefore their reflections in time were coming and sitting on top of each other, and so the receiver was not able to make out whether how many paths are really there. Now when I transmit this pulse-on from the transmitter, at the receiver, when I see the signal in the time domain, again it's a problem, because again in the time domain your red and blue will sit on top of each other. There is no way you can distinguish them in time. But if I observe my received response in the frequency domain, so this is what you are transmitting this is the frequency domain representation of what you have transmitted. But in the frequency domain, what will happen is reflector 1 does not do anything because its Doppler is 0. So you get the red exactly at 0, nu p, 2 nu p, 3 nu p, like that. But what you get from this blue reflector will be shifted by nu 2, because it has this reflector 2 is inducing a Doppler shift of nu 2, and so your pulses will now be received at nu 2, nu 2 plus nu p, and like that. Okay. So now in the frequency domain you can separate them out. So that's the idea why this is very useful. By doing this kind of a quasi localization simultaneously in time and frequency, you can separate out these paths. And the same thing when you have, let's say there are two reflectors, okay, they have the same Doppler. So they have the same relative speed v, and because of which in the frequency you cannot separate them out because they have the same Dopplers. But because they have different delays, in time they can be separated. Okay. So therefore I come to this representation which I will be using very heavily. I mean, this is a known thing. I mean, everybody knows that that the channel has this delay Doppler representation. Okay. So in the delay Doppler representation, you basically have something which is called as the delay Doppler spreading function of the channel. Remember this thing. What is this? This is the response of the channel, of a channel path which introduces a delay of tau, and I think there is a mistake here, it should be nu here actually. So somebody can note down, I will change it. So instead of Fc it should be nu here, okay, nu, because this is the Doppler shift, right. So if this is the response if the channel is introducing a delay of tau seconds and a Doppler shift of nu hertz, okay. And then this is the weighing factor, and then you sum all of them up, okay. So the meaning of this thing is basically it's like a it tells you how much is the delay Doppler spread in the channel. I mean, which are the delay Doppler what are the delay Doppler shifts of the paths in the channel, okay. So for my example where I had 4 paths, this is the delay Doppler spreading function. I mean, I have paths which are having for example, the first path has a delay of tau 1 and a Doppler shift of nu 1, okay. And this is how I represent it in the delay Doppler domain. So the delay Doppler domain is a delay domain and a Doppler domain. It's a 2-dimensional domain basically. But see, this channel representation is already known. I mean, there is nothing new in this, okay. Delay Doppler representation, just like you have time frequency representation, you have the delay Doppler representation of the channel also. It's a known thing, it's nothing new about it. Okay.
That's the one question for the previous slide.
Yeah.
Your channel gain HI, that's just a complex number.
It's a complex number.
It has nothing to do with the
No.
time UI.
It might, if I go back here, it will depend, right? It will depend, but I mean, for example, here in this model, it depends on the carrier frequency, the delay, and the Doppler. Okay, so it does depend.
So even if when it was plotted on the delay Doppler grid, the complex gain itself is a function of the delay and Doppler.
Yes,
right?
yes. But the assumption in this entire course is during your packet transmission, the delay and Doppler is not changing for each path. Okay, they are static. Okay, so as long as that is true, HI is also fixed. Okay, so that's the nice thing about this delay Doppler representation, that if your delays and Dopplers are not changing, then you have a kind of a stationary channel, right? Whereas in the time frequency, domain representation, it's changing in time and in frequency, but here it's not changing, right? It's stationary. So that's another very nice thing about it. This is, I wanted to bring out twisted convolution in a very natural way. See, in your LTI channels which have delay only, okay, if you have two channels H1 and H2 and you know their impulse response and you cascade them, so you have the output of one channel going as input to the other channel, right? Then you know that we can represent this cascade as a single LTI channel whose impulse response is given by the convolution of the impulse responses, right? So something like that is true here also, very interestingly. It's just that, so when I have, so let's say this is the input to the channel, this is the output, but the channel is actually a cascade of two channels, okay? The first channel is having delay Doppler spreading function H1 tau nu. The second channel has a delay Doppler spreading function H2. Now this whole channel from xt to yt is also a doubly spread linear time varying channel, and so this H tau nu is the delay Doppler spreading function of the cascade, and that is given by a convolution of H2 with H1. But this convolution is, first of all, it's in 2 dimensions, and secondly, it's not your linear convolution. Okay, so this is the formula here. So firstly, your output yt is given by this expression here. Okay, I mean, this is the input output relation, where this H tau nu is basically your, I think we just saw this on the previous slide here, right? So I mean, this is my H tau nu. Okay, so this is the channel model. When you have a doubly spread channel, I mean, if your input is xt, this is the output. Okay, so we need to remember this equation is very, very important. Okay. And when you have a cascade, then the effective H tau nu is given by a twisted convolution, and of course here it should actually be H2 first and H1 later on. This is the general formula for H1 followed by H2. So actually this one is when you have H1 here and H2 here, because twisted convolution is not commutative, that's why. Okay, but this is the general formula. I mean, H1 twisted convolved with H2 is given by this double integral. Okay, I mean, if you don't have this term over here, then it looks more like a 2-dimensional convolution, right? But this term is important, and that makes it different from 2-dimensional convolution. We call it twisted convolution. So twisted convolution is the natural way by which the channels interact with each other, and later on we'll see that it's also the way by which input interacts with the channel. Of course, when you have a delay only channel, there's no Doppler shift, then your delay Doppler spreading function becomes of this type. You have a Dirac delta along Doppler because you don't have any Doppler, right? And this is like your impulse response of the usual LTI channels, right? And you can now, if you can use this equation which I had on the previous slide, and if you replace this h tau nu with this, and you get this integral, but because you have delta nu, one of the integrals will just collapse, okay, and what remains is this thing. But this is your convolution that you already know, right? So basically twisted convolution is something like a generalization of, so what linear convolution does for LTI channels, twisted convolution does for doubly spread channels. That's what I showed here. I mean, if you have a cascade of two LTI channels, then the resulting channel is also LTI with this is the impulse response, okay. But this thing is already known to you. So I brought a copy of my book, okay. So this is the textbook which is displayed there. So this chapter 2 of this book has this entire theory with all the details, theorems, appendices containing the proofs, lot of examples. That entire second chapter itself is around 100 pages. And if somebody has the patience to read it, he'll become an expert on Zach OTFS for sure. Okay. Also, if you go to the web page, which is here, this particular link here, then there are MATLAB programs which will help you. So you can take those MATLAB programs and it will help you to understand what Zach OTFS is. All those MATLAB programs were used to generate the figures in that chapter 2. So see, the delay Doppler representation of the channel was known earlier, but what we have introduced as new is delay Doppler representation of a signal. These are two different things, right? And that was not known earlier actually. So and for that we use Zach transform, okay. Just like Fourier transform gives the frequency domain representation of a time domain signal, Zach transform gives you the delay Doppler representation of a time domain signal. Conceptually it's very simple to understand. So this entire Zach OTFS modulation and signal processing in the delay Doppler domain is based on Zach transform essentially. In the same book, chapter 8 in the appendix, I have this discrete implementation of Zach OTFS. How would you implement it on a real system? And chapter 10 is about using Zach OTFS for radar. A bit of a history. So OTFS was invented by Dr. Ronnie Hadani. He is at UT Austin in USA. He is a co-founder of a company called Cohere Technologies, and the first paper appeared around 2017. But this version of OTFS is not what I am talking about today and tomorrow. This version of OTFS, I call it OTFS 1.0, was made to be compatible with 4G and 5G modems, but it's not, this waveform is not predictable. And so when the Doppler really becomes high, 4, 5, 6, for 1, 2, 3 kilohertz, it will give you much better performance than OFDM. But when you make it like 5, 6, 7, then you have a problem. Then even this does not work that great, okay. And now independently I was, so it was around the COVID time, 2020, I got some time and I had seen this paper 2017 and I knew a bit about Zach transform. So I started working on this thing. And so you will see my paper in 2021 where I propose a receiver which is made entirely on Zach transform, okay. But the transmitter is still MC OTFS, so it was kind of a mix. And so these two papers, those were my initial works. And then of course I came in touch with Professor Hadani, and we have been just collaborating. He's also an author. He's the second author on this book, if you see. And then I am also a member of the technical advisory board of Cohere Technologies. And right now we are trying to see if we can push this waveform at least as a study item in the 6G standardization. Yeah. So, and then there is this paper, okay, which is like the first paper on ZARC OTFS, where both transmitter and receiver is ZARC OTFS. And then since then, I have not listed many, but there are a lot of over-there implementations which have come up, I mean, and which have demonstrated, the feasibility of, ZARC OTFS being robust to high Dopplers compared to CP OFDM. So that will be the end of this session. You want to take a break now, or okay? Okay.